74,000 years ago, the sky turned black across half the planet. In a matter of hours, 2,800 cubic kilometers of rock and ash exploded into the atmosphere. The sun vanished for weeks. Global temperatures plummeted by 15 degrees. Forests died. Rivers froze in places that had never known ice. The human species your ancestors mined was reduced to fewer than 10,000 individuals scattered across the continents. We came within a statistical whisper of extinction. Not from war, not from disease, from a single volcanic eruption in what is now Indonesia. The Earth has done this before. And it will do this again. Right now, beneath Yellowstone National Park, beneath the streets of Naples, beneath the tranquil waters of Lake Toba, massive chambers of molten rock are accumulating. Pressure is building, the crust is fracturing. The question is not if these volcanoes will erupt. The question is when, and whether we will be ready. The sleeping giants. The earth beneath our feet is not the solid, unchanging foundation we imagine it to be. It breathes, it shifts. And in certain places scattered across our planet, it waits with a patience that spans millennia, holding within its depths forces so immense that they have, throughout history, reshaped continents and altered the course of human civilization. We call them supervolcanoes. The term itself barely captures the magnitude of what these geological features represent. Unlike the classic cone-shaped mountains that come to mind when we think of volcanoes, supervolcanoes often hide in plain sight. They are calderas, vast depressions in the earth crust formed by previous eruptions so catastrophic that the ground itself collapsed into the emptied magma chambers below. The definition is precise. A supervolcano is any volcanic system capable of producing an eruption with an ejecta volume greater than 1,000 cubic kilometers. To put this in perspective, the 1980 eruption of Mount St. Helens released approximately 1 cubic kilometer of material. A supervolcanic eruption would be 1,000 times more powerful, at minimum. There are roughly 20 known supervolcanic systems on Earth today. Some are famous: Yellowstone in the United States, Toba in Indonesia, Taupo in New Zealand. Others remain obscure, known primarily to volcanologists who study them with a mixture of scientific fascination and quiet apprehension. Each one represents a potential extinction-level event, a reminder that despite all our technological advancement, we remain vulnerable to forces we can monitor but cannot control. The geological record tells us that supervolcanic eruptions occur, on average, once every 100,000 years. The last major eruption was Toba, approximately 74,000 years ago. The evidence suggests it came terrifyingly close to ending our species entirely. Genetic studies indicate that the human population may have been reduced to as few as 3,000 to 10,000 individuals in the aftermath, creating what scientists call a population bottleneck. We are all descendants of those survivors. What makes these systems so dangerous is not merely their size, but their unpredictability. Unlike conventional volcanoes, which often provide warning signs before eruption, supervolcanoes can remain dormant for hundreds of thousands of years, showing little surface activity even as massive magma chambers grow beneath them. The ground may rise imperceptibly. Hot springs may form or change temperature. Small earthquakes may occur with increasing frequency. But these signs can be subtle, ambiguous, easily dismissed until it is far too late. The mechanism is deceptively simple. Deep beneath the surface, typically 5 to 15 kilometers down, magma accumulates in vast underground reservoirs. This magma is exceptionally rich in silica, making it thick, viscous, and capable of trapping enormous amounts of dissolved gases. As more magma enters the chamber over thousands of years, pressure builds. The rock above flexes and fractures. Eventually, when the pressure exceeds the strength of the overlying rock, the chamber ruptures. What follows is almost beyond comprehension. In a conventional volcanic eruption, lava flows from a vent. In a supervolcanic eruption, the entire landscape explodes. Pyroclastic flows, superheated avalanches of gas, ash, and rock fragments traveling at speeds exceeding 700 kilometers per hour, race across the terrain, incinerating everything in their path. The eruption column can reach 50 kilometers into the stratosphere, injecting billions of tons of ash and sulfur dioxide into the upper atmosphere. The immediate devastation is only the beginning. The ash spreads across continents, burying entire regions under meters of suffocating tephra. Agriculture becomes impossible across vast areas. The sulfur dioxide reacts with water vapor to form sulfuric acid aerosols that encircle the planet, reflecting sunlight back into space. Global temperatures plummet. This is volcanic winter, a phenomenon that can last for years or even decades, triggering crop failures, famine, and mass extinction events. Yet here is the unsettling truth that keeps volcanologists awake at night. We have never witnessed a supervolcanic eruption in recorded history. Everything we know comes from geological evidence, computer models, and mathematical projections. We are theorizing about continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. Beneath the breathtaking beauty of Yellowstone National Park, with its geysers, hot springs, and abundant wildlife, lies a force of unimaginable power. This isn't just a park. It's the site of one of the largest active volcanoes on the planet, a ticking time bomb that scientists are watching with intense focus. Welcome to the world of supervolcanoes. What you see on the surface at Yellowstone, Old Faithful, the Grand Prismatic Spring, these are all just symptoms. They're the visible signs of a massive magma chamber simmering just a few kilometers beneath your feet. This isn't your average volcano. The Yellowstone hotspot is a colossal plume of superheated rock rising from deep within the earth, possibly from the very boundary of the mantle and the core, nearly 3,000 kilometers down. Think of it like a blowtorch held stationary beneath a moving sheet of metal. As the North American tectonic plate slowly drifts southwest, this fiery plume burns through the crust, leaving a trail of destruction in its wake. We can see this trail today, a series of ancient volcanic craters stretching across Idaho and Oregon, a breadcrumb path leading directly to Yellowstone. The park's history is written in cataclysm. 3 supereruptions have defined its past. The first, 2.1 million years ago, was an event of almost incomprehensible scale, spewing out 2,500 cubic kilometers of rock and ash. The most recent major event, about 640,000 years ago, was responsible for creating the massive crater, or caldera, that forms the heart of the park today, a depression measuring a staggering 55 by 72 kilometers. This eruption ejected 1,000 cubic kilometers of material, blanketing much of North America in a thick layer of volcanic ash and plunging the globe into a volcanic winter. Looking at the timing, 2.1 million, 1.3 million, and 640,000 years ago, it's easy to get worried and think we're overdue for the next big one. But geology isn't like a train schedule. Volcanologists are quick to point out that there's no evidence to suggest an eruption is coming in our lifetimes, or even in the next few thousand years. Still, what lies beneath is enough to keep them busy. Using advanced seismic imaging, scientists have discovered not one, but 2 magma reservoirs under Yellowstone. The upper chamber, closer to the surface, contains a massive amount of material, but only about 5 to 15% of it is actually molten and eruptible. Beneath that lies a second, much larger reservoir, a behemoth containing 46,000 cubic kilometers of mostly solid and partially molten rock. The sheer scale is mind-boggling. To keep an eye on this sleeping giant, Yellowstone has one of the most sophisticated monitoring systems in the world. A dense network of seismometers tracks the thousands of tiny earthquakes that happen each year, offering clues about the movement of magma and superheated water below ground. High-precision GPS stations measure the ground's movement down to the millimeter, detecting the subtle breathing of the caldera as it rises and falls. Gas sensors constantly analyze the air for changes in chemical compounds that could signal fresh magma rising from the depths. And the caldera definitely breathes. Between 2004 and 2010, the ground swelled upwards by about 25 centimeters, the fastest rate ever recorded before slowing and sinking again. This is normal behavior for a living volcano, driven by shifts in magma and hydrothermal fluids deep below. It's a sign that the system is active, but not necessarily that it's about to blow. So what would be the real warning signs? Scientists have a pretty good idea. We'd likely see a dramatic swarm of earthquakes, hundreds of significant tremors a day. The ground would start to deform rapidly, rising by meters over just weeks or months. We'd see huge changes in the geysers and hot springs, and a massive spike in the release of volcanic gases like sulfur dioxide. The good news is, these signs would likely give us months, if not years, of warning. But Yellowstone doesn't have to have a supereruption to be dangerous. A much more likely scenario is a smaller, but still powerful lava flow. The last one happened about 70,000 years ago. An event like that wouldn't cause a global catastrophe, but it would be devastating on a regional scale, destroying one of America's most beloved landscapes and forcing the evacuation of millions. Across the Atlantic, another, perhaps even more urgent, threat is stirring. In the beautiful Bay of Naples, Italy, in the shadow of the infamous Mount Vesuvius, lies a danger many have never even heard of: Campi Flegrei, or the burning fields. This isn't a single mountain but a sprawling, 13-kilometer-wide supervolcano, and 500,000 people live directly inside its caldera. Another 3 million live in the greater Naples area. They are all living on top of what might be the most dangerous volcano in the world. For the past 70 years, Campi Flegrei has been in a state of unrest. The ground has been rising and falling in a cycle known as bradyseism. In the early 1980s, the ground lifted by nearly 2 meters, forcing the evacuation of an entire town. After a period of calm, the uplift started again in 2005 and hasn't stopped. The ground is now more than a meter higher than it was just 2 decades ago. This constant movement is straining the Earth's crust. Scientists at Italy's National Institute of Geophysics and Volcanology are watching with growing concern. They believe the crust is being stretched to its breaking point. Thousands of small earthquakes are shaking the region every month, a clear sign of the stress building up below. The question isn't if the crust will rupture, but when. When it does, there are a few possibilities. The built-up pressure could release a massive burst of hot gas and steam in what is known as a phreatic eruption. Or, even worse, the rupture could open a path for magma to reach the surface. The people of Naples are living with this reality every day. Unlike Yellowstone, where an eruption feels like a distant, abstract threat, the danger at Campi Flegrei is immediate and tangible. The ground is literally moving beneath their feet. The Italian government has updated its emergency plans, acknowledging the increasing risk. These plans involve the potential evacuation of hundreds of thousands of people, a logistical nightmare in one of Europe's most densely populated regions. For the scientists monitoring Campi Flegrei, it is a race against time to understand the volcano's behavior and provide the warnings needed to save lives. From the pristine wilderness of Wyoming to the crowded coast of Italy, these supervolcanoes remind us of the immense power hidden just beneath the surface of our planet. They are not relics of a distant past, but active, breathing systems that shape our world and pose a continuing, if uncertain, risk. By studying them, we not only protect the people living in their shadow, but also gain a deeper understanding of the incredible forces that have forged the Earth we call home. Thanks for watching. If you found this fascinating, don't forget to like, subscribe, and hit the bell for more deep dives into our amazing world. Have you ever heard of a supervolcano? These aren't your typical cone-shaped mountains spitting lava. These are colossal hidden giants sleeping just beneath the surface, with the power to reshape our world. Today, we're re-diving deep into the fiery heart of 2 of the most dangerous supervolcanoes on Earth, Campi Flegrei in Italy and Toba in Indonesia. What would happen if they woke up? Let's start in Italy, near the bustling city of Naples. Most people know about Vesuvius, the volcano that buried Pompeii. But just a few miles away lies a much larger and more volatile threat, Campi Flegrei, which means burning fields. It's not a single mountain, but a vast, sprawling caldera, a sunken basin 12 kilometers wide, mostly hidden underwater in the Bay of Naples. This entire area, home to over 500,000 people, is essentially the top of an active, breathing supervolcano. The history of Campi Flegrei is written in layers of ash and rock. Its most cataclysmic event was the Campanian ignimbrite eruption, about 39,000 years ago. This was the largest volcanic eruption in Europe in the last 200,000 years. It was apocalyptic. The volcano ejected an unimaginable 300 cubic kilometers of magma, blanketing an area of 15,000 square kilometers in a thick layer of tuff. Ash from this eruption has been found as far away as Greenland. It plunged Europe into a volcanic winter, a period of severe cold that lasted for years, drastically altering the climate and possibly contributing to the decline of the Neanderthals. Imagine a sky so dark with ash that the sun disappears not for a day, but for years. Fast forward to about 15,000 years ago, and Campi Flegrei erupted again in a major event known as the Neapolitan Yellow Tuff eruption. While not as massive as the Campanian ignimbrite, it was still enormous. It sculpted the modern landscape around Naples, creating the very ground on which millions of people now live. It's a stark reminder that this seemingly peaceful area has a history of violent transformation. But Campi Flegrei's activity isn't just ancient history, it's happening right now. The key phenomenon to watch here is called bradyseism. This is the gradual rising and falling of the ground as the magma chamber beneath fills or empties. The ancient Roman market in the town of Pozzuoli, known as the Temple of Serapis, acts as a natural geological measuring stick. Its stone columns are pocked with holes drilled by marine mollusks. These holes show that over centuries the temple has been submerged by the sea and then lifted back out of the water as the ground level changed. It's a silent, slow-motion dance between the land and the sea, driven by the restless magma below. In recent decades, this dance has become much more alarming. Between 1969 and 1972, and again between 1982 and 1984, the ground at Pozzuoli rose dramatically by more than 3 meters in total. This period of rapid uplift was accompanied by thousands of small earthquakes, causing widespread panic and forcing the evacuation of 40,000 residents. The ground was literally swelling like a blister, a clear sign that magma or hot volcanic gases were pushing up from below. After a period of quiet sinking, the ground started rising again in 2005. This new phase of uplift has been slower but continuous, raising concerns among scientists. Since 2012, the volcano has been on yellow alert, meaning it requires constant, intensive monitoring. In recent years, the frequency and intensity of earthquakes have been increasing. In late 2023 and early 2024, the region has been shaken by the strongest swarms of tremors in 40 years, keeping residents on edge. The question isn't if Campi Flegrei will erupt again, but when and how big it will be. An eruption today would be a humanitarian catastrophe of unimaginable proportions. Now let's travel halfway across the world to the island of Sumatra in Indonesia, to a place that looks like a tropical paradise, Lake Toba. This stunningly beautiful lake, over 100 kilometers long and 30 kilometers wide, is not a normal lake. It fills the caldera of the Toba supervolcano. And the story of its creation is one of the most terrifying chapters in our planet's recent geological history. Around 74,000 years ago, Toba exploded in one of the largest known eruptions on Earth. It's classified as a magnitude 8 event on the Volcano Explosivity Index, the highest possible rating. The scale of this eruption is difficult to comprehend. It spewed out an estimated 2,800 cubic kilometers of rock and ash. That's nearly 10 times more than the Campanian ignimbrite eruption and thousands of times larger than the 1980 eruption of Mount St. Helens. The immediate aftermath was devastating. Pyroclastic flows, superheated currents of gas, ash, and rock would have annihilated everything for hundreds of kilometers around. A blanket of ash, up to 6 meters thick, covered vast areas of Southeast Asia. Traces of this ash have been found all over the globe, from the South China Sea to the Arabian Sea and even in Africa. But the long-term effects were even more catastrophic. The sheer volume of sulfur dioxide and ash injected into the stratosphere blocked out sunlight, triggering a global volcanic winter that may have lasted for 6 to 10 years. Global temperatures are thought to have plummeted by as much as 15 degrees Celsius. This sudden and dramatic climate change would have caused widespread crop failures and ecosystem collapse. This brings us to the Toba catastrophe theory. Some scientists propose that this event caused a near-extinction-level event for humanity. They argue that the sudden deep freeze and its consequences decimated the early human population, reducing it to just a few thousand individuals. According to this theory, all humans alive today are descendants of this small group of survivors. While this theory is still debated, with some evidence suggesting human populations were more resilient, there's no doubt that the Toba eruption was a profound shock to the global system and a formidable challenge for our ancestors. The terrifying part? Toba is not extinct. The ground in the caldera is slowly rising, and a new volcanic cone called Pusik Bohet has formed on the edge of the caldera, indicating that magma is still active deep beneath the serene waters of the lake. Like Campi Flegrei, it is a sleeping giant. So what have we learned? Supervolcanoes like Campi Flegrei and Toba operate on geological timescales that are hard for us to grasp. They can lie dormant for tens of thousands of years, lulling us into a false sense of security. But the signs of unrest at Campi Flegrei, The rising ground, the constant earthquakes, are a powerful reminder that the forces that shaped our planet's past are still very much active today. Scientists are monitoring these giants with an arsenal of modern technology, from GPS stations and seismometers to gas monitoring and satellite imagery. They are working tirelessly to understand the signals these volcanoes send, hoping to provide timely warnings if an eruption becomes imminent. But the challenge is immense. The scale of a potential eruption from either of these volcanoes would overwhelm any disaster response plan we could devise. These simmering giants remind us of the incredible power of our planet. They are a testament to the fact that we live on a dynamic, ever-changing world where the ground beneath our feet is not as solid as it seems. It's a humbling thought and a crucial one for our future. Thanks for joining me on this deep dive into the world of supervolcanoes. If you found this fascinating, don't forget to like, subscribe, and hit that notification bell so you don't miss our next exploration into the wonders and dangers of our world. Stay curious and stay safe. The ash fell across an area spanning millions of square kilometers. Deposits 15 centimeters thick have been found in India, 3,000 kilometers from the eruption site. Ash layers from Toba appear in sediment cores from the South China Sea, the Indian Ocean, and even East Africa. The Middle East was covered in a blanket of volcanic ash. For weeks, perhaps months, the sun would have been obscured across much of the eastern hemisphere. But the ash was only the beginning. The sulfur dioxide released by the eruption, estimated at billions of tons, reacted with water vapor in the stratosphere to form sulfuric acid aerosols. These microscopic droplets remained suspended in the upper atmosphere for years, forming a reflective veil that scattered incoming sunlight back into space. Global temperatures plummeted. Ice core data from Greenland suggests a cooling of 3 to 5 degrees Celsius globally, with some models proposing drops of up to 15 degrees Celsius in certain regions. This is volcanic winter in its most extreme form. Growing seasons would have shortened drastically or disappeared entirely in many areas. Forests would have died back. Water sources would have frozen in regions unaccustomed to such cold. The ecological disruption would have cascaded through food chains, causing mass extinctions among species unable to adapt quickly enough to the sudden climate shift. The impact on early human populations remains one of the most controversial topics in paleoanthropology. In 1998, anthropologist Stanley Ambrose proposed the Toba catastrophe theory, suggesting that the eruption created a population bottleneck that reduced the global human population to between 3,000 and 10,000 individuals. Genetic evidence shows a marked reduction in human genetic diversity around this time, consistent with a severe population crash. The theory suggests we came within a statistical whisper of extinction. However, the evidence is not conclusive. Archaeological sites in India dating to the period immediately after the Toba eruption show signs of continued human habitation. Stone tools found both below and above the ash layer suggest that at least some populations survived locally and maintained their cultural practices. Some researchers argue that while Toba certainly caused significant hardship, human adaptability and behavioral flexibility allowed scattered populations to endure. Recent genetic studies have complicated the picture further. While a population bottleneck did occur around 74,000 years ago, some geneticists question whether it can be attributed solely to Toba. Climate data shows that Earth was already in a cooling phase prior to the eruption, part of the broader glacial period. Toba may have intensified an existing crisis rather than creating one from scratch. Disentangling the volcanic effects from the background climate trends remains challenging. What is not in dispute is the eruption's geological legacy. The Toba caldera today contains a resurgent dome, Samosir Island, which has risen from the caldera floor as magma continues to accumulate beneath. This process of resurgence is common in large calderas and indicates that the volcanic system remains active. Small earthquakes occur regularly. Hot springs and fumaroles around the lake testify to the heat still present at shallow depths. The magma chamber beneath Toba is gradually recharging. Seismic studies reveal a large body of partially molten rock at depths of 7 to 15 kilometers beneath the caldera. The rate of magma accumulation is slow, measured in cubic kilometers per millennium rather than per century, but it is persistent. Given enough time, tens or hundreds of thousands of years, conditions could develop for another supereruption. The Indonesian government, in cooperation with international volcanological institutions, maintains a monitoring network around Toba. Seismometers track earthquake activity. GPS stations measure ground deformation. Yet the monitoring is nowhere near as comprehensive as that at Yellowstone or Campi Flegrei, partly due to resource constraints and partly because the perceived immediate threat is lower. Toba shows none of the dramatic unrest characterizing Campi Flegrei. It sleeps, but it is not dead. The Toba eruption serves as a sobering reminder that supervolcanic events are not merely geological curiosities but forces, capable of reshaping the course of life on Earth. They operate on timescales that dwarf human history, yet when they awaken, their effects are immediate and global. We cannot prevent such eruptions. We can only study them, learn from their past behavior, and prepare as best we can for an eventuality that remains for now mercifully distant. In 1982, volcanologists Christopher Newhall and Stephen Self introduced a system that would fundamentally change how we understand and communicate volcanic hazards. The Volcanic Explosivity Index, or VEI, provides a standardized scale for measuring the magnitude of explosive volcanic eruptions, ranging from 0 to 8. Like the Richter scale for earthquakes, the VEI is logarithmic, meaning each increase in number represents a tenfold increase in erupted material and explosive power. The scale begins modestly. A V0 eruption is non-explosive, characterized by gentle effusive activity, where lava flows peacefully from a vent. Hawaiian volcanoes like Kilauea typically produce 0 or 1 eruptions. These events, while potentially destructive to local infrastructure, pose minimal threat to human life for those who heed warnings and evacuation orders. The lava advances slowly enough that people can walk away from it. V2 eruptions are explosive but relatively small, ejecting between 0.001 and 0.01 cubic kilometers of material. These occur somewhere on Earth several times per year. V3 eruptions are severe, producing 0.01 to 0.1 cubic kilometers of tephra and generating eruption columns that can reach 3 to 15 kilometers in height. These happen multiple times per decade globally. They cause significant local destruction, but rarely affect areas beyond a few dozen kilometers from the volcano. Volcanoes. Forces of nature so powerful they can reshape our world in an instant. But how do we measure the sheer scale of their fury? Scientists use a scale called the Volcanic Explosivity Index, or VEI. It's like the Richter scale for earthquakes, but for volcanoes, ranging from 0 for gentle lava flows to a catastrophic 8. Today, we're diving deep into the VEI, exploring what each level means for our planet and our civilization, from historical disasters to the sleeping giants that could awaken at any time. Let's start with an eruption many Americans remember. Mount St. Helens in 1980. This event was a VA5. It ejected about 1 cubic kilometer of rock and ash, sending a plume 24 kilometers into the sky. A devastating lateral blast flattened 600 square kilometers of forest. 57 people lost their lives, and the eruption caused over $1 billion in damage, disrupting air travel across the continent. For the United States, it was a national catastrophe. But on the global scale of volcanic power, it was only moderate. Now let's climb the ladder to VA6. These eruptions are 10 times larger than a VA5, releasing between 10 and 100 cubic kilometers of material. They happen, on average, just once a century. A recent example was the 1991 eruption of Mount Pinatubo in the Philippines. It blasted 10 cubic kilometers of material into the atmosphere, creating a colossal cloud of ash and gas. Despite a massive and successful evacuation effort, 847 people were killed. The eruption was so powerful it had a global impact, injecting so much sulfur dioxide into the stratosphere that it lowered global temperatures by 0.5 degree Celsius for 2 years. For hundreds of thousands of people, their homes and livelihoods were destroyed, rendering vast areas uninhabitable for years to come. Moving up to VA7, we enter the realm of truly catastrophic events. These eruptions unleash 100 to 1,000 cubic kilometers of material and have profound global consequences. They occur roughly once every 1,000 years. The last one was the 1815 eruption of Mount Tambora in Indonesia. It was the most powerful eruption in recorded human history, ejecting an estimated 160 cubic kilometers of material. The immediate effects were horrifying. At least 71,000 people were killed by pyroclastic flows and choking ashfall. But the nightmare didn't end there. Tambora triggered a global climate crisis. The following year, 1816, became infamous as the year without a summer. Snow fell in New England in June, crops failed across Europe and North America. Widespread famine and disease outbreaks followed, with some estimates suggesting the total death toll from these secondary effects reached hundreds of thousands. And then there's VA8. These are the supereruptions events that eject more than 1,000 cubic kilometers of material. They are true extinction-level events, capable of altering the course of life on Earth. We haven't seen one in human history, but the geologic record is clear. The Toba eruption in Indonesia 74,000 years ago was a VA8. It plunged the planet into a volcanic winter that some scientists believe created a genetic bottleneck in our own species. Here in the United States, the Yellowstone supervolcano has had 3 VA eruptions over the past 2.1 million years. These titans of geology erupt on average once every 100,000 years, though the timing is highly irregular. When scientists say Yellowstone is capable of a VA8 eruption, they aren't being dramatic. They are stating a geological fact based on its history. It's clear the VA is an invaluable tool for understanding volcanic history, but it has its limits. The scale only measures the volume of erupted material, not the eruption's intensity or the specific hazards it creates. A small eruption near a major city could be far deadlier than a massive one in a remote, unpopulated area. The VA also doesn't account for the type of magma, which determines if an eruption is explosive or a calmer, effusive lava flow. It doesn't measure how long an eruption lasts. Some can simmer for months or even years. Perhaps its biggest limitation is that the final VA value can only be assigned after the eruption is over, once scientists have analyzed all the data. During an active eruption, when that information is most crucial for emergency responders, the VA offers limited real-time guidance. Instead, volcanologists must rely on a constant stream of monitoring data from ground shaking to gas emissions to forecast what might happen next. So, how often do these different eruptions happen? There's a clear pattern. Small eruptions are common and big ones are rare. Globally, we see dozens of VA3 events every year. VA4 South happens several times a year. As we saw, VA5 South occur about once a decade, VA6 South once a century, and VA7 South once a millennium. This predictable frequency reflects the fundamental physics of how magma slowly accumulates in chambers deep beneath the Earth, as crust over vast stretches of time. The economic costs also scale dramatically with the VEI. A VE4 might cause tens of millions of dollars in damage. A VE5, like Mount St. Helens, can cost billions. A VE6, like Pinatubo, can destabilize the entire economy of a nation. A VE7, like Tambora, would have global economic impacts measured in the trillions of dollars, triggering a worldwide recession. And a V8 supereruption? The economic cost becomes almost meaningless. It would effectively halt modern civilization as we know it, at least for a time. The focus wouldn't be on economies, it would be on pure survival. Understanding this scale helps us contextualize the threat posed by the volcanoes we monitor today. But there's one supervolcano in the United States that many people have never even heard of. It's not Yellowstone. It lies in the eastern Sierra Nevada of California, just south of Yosemite National Park. It's called the Long Valley Caldera. This massive 32-kilometer-long depression in the Earth was formed 760,000 years ago by a cataclysmic eruption. It ejected approximately 600 cubic kilometers of material, putting it on the high end of a VA7, right on the cusp of a VA8 supereruption. Geologists call the resulting volcanic deposit the Bishop Tuff. It blankets huge swaths of eastern California and Nevada. Ash from that single eruption has been found as far away as Nebraska. The eruption column would have towered 40 to 50 kilometers into the atmosphere, injecting enough ash and gas to cause a severe global volcanic winter. Today, the landscape inside the Long Valley Caldera seems deceptively calm and beautiful. The popular ski resort town of Mammoth Lakes sits directly on the caldera's southern rim. About 8,000 people live there year-round, but that population swells to over 30,000 during tourist season. Visitors flock to the area for its world-class skiing, hiking, and natural hot springs. Very few of them realize they are vacationing directly on top of one of the most intensely monitored and potentially dangerous volcanic systems in the world. The question is not whether another massive eruption will happen on our planet, but when, where, and weather will be ready. The Volcanic Explosivity Index gives us the language to understand the scale of the threat, connecting the disasters of the past to the risks of the future. By studying these immense forces, we can better prepare for them, working to protect lives in our global society from the awesome power that lies just beneath our feet. Thanks for watching. If you found this journey into the world of volcanoes fascinating, please consider liking this video and subscribing for more deep dives into the science that shapes our world. Stay curious and stay safe. The modern era of concern began in 1978 when a magnitude 5.4 earthquake struck the region, followed by 3 more magnitude 5 earthquakes over the next 2 years. Seismologists noted something unusual. The earthquakes were occurring in swarms, clusters of hundreds or thousands of small to moderate quakes concentrated in specific areas, rather than following the typical main shock aftershock pattern. This suggested movement of magma or hydrothermal fluids beneath the surface. Then the ground began to rise. Between 1979 and 1984, the resurgent dome in the center of the caldera, an area known as the Mammoth Knolls, uplifted by approximately 80 centimeters. Leveling surveys and newly installed GPS stations confirmed what seemed almost impossible. A significant portion of the caldera floor was inflating at rates of 10 to 20 centimeters per year. The implications were clear. Magma was accumulating beneath Long Valley. In May 1980, just days after Mount St. Helens erupted in Washington, 4 magnitude 6 earthquakes struck the south side of the Long Valley caldera within a 48-hour period. The timing was purely coincidental, but the psychological impact on local residents was profound. The USGS issued a notice of potential volcanic hazard, the first such notice ever released for a volcanic system in the United States outside of Alaska and Hawaii. Tourism plummeted. Property values collapsed. Residents debated whether to evacuate. The crisis intensified when carbon dioxide began killing trees on Mammoth Mountain, a young volcano on the southwest edge of the caldera. Soil gas measurements revealed that CO2 concentrations in some areas exceeded 90%, lethal to both vegetation and animals. The gas was seeping up through the soil from magma degassing at depth. In 2006, 3 ski patrol members fell into a snow-covered fumarole and died from asphyxiation caused by volcanic gases. The danger was not theoretical. The source of the unrest gradually became clearer through seismic imaging and geophysical studies. Approximately 8 kilometers beneath the resurgent dome lies a body of partially molten rock, a magma chamber with an estimated volume of 240 cubic kilometers. Only a small fraction, perhaps 15 to 27%, is actually molten, but that still represents tens of cubic kilometers of eruptible magma. Additional magma is present at greater depths, extending down to 30 kilometers or more. The uplift that began in 1979 slowed and eventually reversed in the mid-1980s, only to resume intermittently over the following decades. The pattern suggests a complex system, where magma intrusion is episodic rather than continuous. Fresh magma rises from depth, stalls, crystallizes partially, releases gases, and causes the ground to rise. As the gases escape and pressure is released, the ground subsides. Then the cycle repeats. This is not the steady march toward an imminent eruption, but rather the normal behavior of a restless caldera. Earthquake swarms continued to plague the region. In 2014, a swarm involving over 1,000 earthquakes occurred beneath Mammoth Mountain. In 2019, another swarm produced over 2,000 earthquakes in a matter of weeks. Most are too small to be felt, but they are meticulously recorded by the extensive monitoring network. Each swarm is analyzed for patterns that might indicate magma movement at depth or changes in the hydrothermal system. The USGS California Volcano Observatory maintains constant surveillance of Long Valley. More than 60 seismometers track earthquake activity. GPS stations measure ground deformation in real time. Satellite radar interferometry provides broad-scale deformation maps. Gas sensors monitor CO2 emissions from the soil and fumaroles. Temperature sensors track thermal changes in hot springs and fumaroles. The data streams continuously to USGS offices where scientists analyze it for signs of escalating unrest. What would an eruption at Long Valley look like? The answer depends on the size and location. A small phreatic eruption, driven by steam rather than magma, could occur with little warning and affect a localized area. A magmatic eruption similar to those that have occurred within the caldera over the past 100,000 years could produce pyroclastic flows, lava domes, and ashfall, affecting the entire eastern Sierra Nevada region. A caldera-forming supereruption, while geologically possible, would require the accumulation of far more eruptible magma than currently exists in the chamber, a process that would likely take tens of thousands of years. The challenge for scientists and emergency managers is communicating uncertainty to a public that desires definitive answers. Long Valley is restless. It will likely remain restless for decades or centuries. It will almost certainly erupt again at some point in the geological future. But translating these long-term certainties into actionable, short-term guidance is extraordinarily difficult when the warning signs are ambiguous and the timescales involved extend beyond human planning horizons. Mount Vesuvius, the volcano that stopped time, on the morning of August 24th in the year 79 AD, the inhabitants of Pompeii went about their daily routines with no sense of impending doom. Merchants opened their shops in the Forum. Bakers prepared bread in their ovens. Children played in the streets. Mount Vesuvius, the mountain that loomed 10 kilometers to the north, had been quiet for as long as anyone could remember. The Romans did not even recognize it as a volcano. The slopes were covered with vineyards. The soil was fertile. Life was prosperous. Then, shortly after midday, the mountain exploded. A column of superheated gas, ash, and pumice erupted from the summit with such force that it reached an estimated height of 33 kilometers within minutes. The eruption column was visible for hundreds of kilometers. Pliny the Younger, watching from across the Bay of Naples, described it as resembling a Mediterranean pine tree, with a tall trunk spreading into branches at the top. His uncle, Pliny the Elder, a Roman naval commander and naturalist, would die attempting to rescue friends from the eruption's path. For the next 18 hours, pumice and ash rained down on Pompeii at a rate of 15 centimeters per hour. Roofs collapsed under the accumulating weight. Those who remained in the city sought shelter in buildings that quickly became death traps. By the time the pumice fall ceased, Pompeii was buried under 2.8 meters of volcanic debris. Most residents had fled during these early hours, but approximately 2,000 people remained, either unable or unwilling to leave. Then came the pyroclastic surges. Shortly after midnight, the eruption column became unstable and collapsed, sending avalanches of superheated gas and ash racing down the mountain at speeds exceeding 100 kilometers per hour. The temperature of these surges reached 300 to 400 degrees Celsius, hot enough to kill instantly but not hot enough to incinerate bodies completely. The victims died from thermal shock and asphyxiation within seconds. Their bodies were buried where they fell, entombed in ash that hardened into rock over the centuries. The nearby town of Herculaneum, located closer to Vesuvius but shielded initially by wind direction, fared differently. The pumice fall there was lighter, only 20 centimeters. Many residents fled during the night. Those who remained sought refuge in stone boathouses along the beach, hoping for rescue by sea. It never came. In the early morning hours of August 25th, a massive pyroclastic flow swept through Herculaneum, traveling at speeds up to 400 kilometers per hour with temperatures exceeding 500 degrees Celsius. The flow instantly vaporized flesh and boiled brain tissue within skulls. More than 300 people died in the boathouses alone, their skeletons discovered centuries later in the exact positions where they had huddled together. The eruption of Vesuvius in 79 AD was a VA5 event, ejecting approximately 4 cubic kilometers of magma. By modern standards, it was moderate. Yet it achieved something no other eruption in history has matched. It preserved 2 Roman cities in near-perfect condition, creating a time capsule that has provided archaeologists with unprecedented insights into daily life in the ancient world. The bodies themselves decayed over the centuries, but the ash that surrounded them hardened into cavities that retained the exact shape of the victims in their final moments. Giuseppe Fiorelli, the Italian archaeologist who excavated Pompeii in the 1860s, developed a technique of injecting plaster into these cavities. The resulting casts are haunting. We see a mother clutching her child, a man covering his face as he tries to breathe, a dog straining against its chain. These are not statistics. They are individuals, captured at the moment of their deaths, their terror and suffering preserved in volcanic stone. Vesuvius has erupted dozens of times since 79 AD. The most recent significant eruption occurred in March 1944. During World War II, Allied forces had recently established airfields near the volcano. When Vesuvius erupted, lava flows destroyed the villages of San Sebastiano and Massa, killing 26 people. Volcanic bombs rained down on American B-25 bombers parked at the Pompeii airfield, destroying or damaging 88 aircraft. The eruption was a VA3 event, far smaller than the 79 AD catastrophe. Yet it served as a reminder that Vesuvius remains active and dangerous. Today, more than 3 million people live within the potential impact zone of a major Vesuvius eruption. The city of Naples has expanded to within a few kilometers of the volcano's base. Towns and villages blanket the slopes. The population density is among the highest near any active volcano in the world. This creates what volcanologists and civil defense officials acknowledge as the most serious volcanic emergency scenario in Europe. The Italian government has developed an evacuation plan for the Vesuvius area, known as the Red Zone, which encompasses approximately 600,000 people living closest to the volcano. The plan assumes that monitoring systems will provide at least 2 weeks warning before a major eruption. During this time, all Red Zone residents would be evacuated to designated regions across Italy. The logistics are staggering: transportation of hundreds of thousands of people, provision of shelter and supplies, maintenance of order during a mass exodus. The plan's assumptions are optimistic. While Vesuvius has been extensively monitored since the early 20th century, with networks of seismometers, GPS stations, and gas sensors blanketing the volcano, translating monitoring data into reliable eruption forecasts remains highly uncertain. The 1944 eruption provided only hours of warning. If the next eruption follows a similar pattern, there may not be 2 weeks. There may not even be 2 days. The volcano shows signs of unrest. Small earthquake swarms occur periodically. The ground deforms slightly as magma and gases move beneath the surface. Fumaroles on the crater floor release volcanic gases. Yet these signs have persisted for decades without culminating in an eruption. Vesuvius is restless, but it has been restless for a very long time. Determining when this restlessness will transition into eruptive activity is the central challenge facing volcanologists working in the Naples region. Monitoring the giants, the science of prediction. The ability to monitor volcanoes has advanced exponentially over the past century, transforming our understanding from folklore and superstition to precise measurements of processes occurring deep within the Earth. Yet despite these technological achievements, predicting exactly when and how a volcano will erupt remains one of the most challenging problems in geoscience. The difference between monitoring and prediction is profound, and understanding this distinction is crucial for appreciating both the capabilities and limitations of modern volcanology. Seismology forms the foundation of volcanic monitoring. Earthquakes accompany nearly all volcanic activity because moving magma fractures rock as it forces its way toward the surface. Modern seismometers can detect ground vibrations so subtle they measure in nanometers, roughly the width of a few atoms. Networks of these instruments surround major volcanic systems, recording thousands of earthquakes per year that are invisible to human perception, but critical for understanding what is happening at depth. Volcanic earthquakes have distinct characteristics that allow scientists to interpret their causes. Volcanotectonic earthquakes result from brittle fracture of rock and produce sharp, high-frequency signals similar to tectonic earthquakes. Long-period earthquakes generate lower-frequency signals and are associated with the movement of fluids, either magma or pressurized gases and water. Harmonic tremor, a continuous vibration that can last for hours or days, indicates sustained fluid movement and often precedes or accompanies eruptions. The ability to distinguish between these earthquake types allows volcanologists to infer whether magma is rising, whether gases are escaping, or whether the system is simply adjusting to tectonic stress. Have you ever wondered what it would be like to stand near a volcano on the verge of eruption? The ground trembles, strange gases fill the air, and a deep rumbling sound comes from within the earth. It's a terrifying and awe-inspiring thought. But for volcanologists, these are clues, vital signs of our planet's fiery heart. Today, we're venturing into the high-stakes world of volcanic forecasting, exploring the incredible science that helps us predict the unpredictable and save thousands of lives. So, how do scientists actually keep an eye on these sleeping giants? It's not about staring into a crater with a pair of binoculars. It's a high-tech surveillance operation. One of the most crucial tools is GPS, just like the one in your phone, but way more precise. Scientists place highly sensitive GPS stations all over a volcano's slopes. As magma, that molten rock from deep within the earth, moves upward, it causes the ground to bulge and stretch. It's like blowing up a balloon under a blanket. These GPS units can detect tiny movements, sometimes just a few millimeters, giving us the first hint that something is brewing underground. But GPS only tells us part of the story. To get a bigger picture, we use a technique called INSAR, which is short for Interferometric Synthetic Aperture Radar. It sounds complicated, but the idea is brilliant. Satellites orbiting Earth take radar images of a volcano's surface. By comparing images taken at different times, scientists can create incredibly detailed maps that show how the ground has deformed. It's like having a planet-wide X-ray that reveals even the slightest swelling or sinking of the land, covering areas that are too remote or dangerous to place GPS equipment. Ground deformation is a huge clue, but what's happening inside the volcano is just as important. As magma rises, it releases gases that were trapped under immense pressure. The most important one scientists look for is sulfur dioxide. You might recognize its sharp, pungent smell like a struck match. Scientists use special instruments called spectrometers to measure the amount of sulfur dioxide coming out of a volcano's vents. A sudden spike in gas emissions is a major red flag. It often means fresh, gas-rich magma is getting dangerously close to the surface, increasing the odds of an explosive eruption. Alongside gas analysis, thermal imaging is another key tool. Using infrared cameras often mounted on helicopters or drones, volcanologists can create heat maps of the volcano. These maps show hot spots where magma is near the surface or where superheated volcanic gases are escaping. New hot spots or existing ones getting hotter can signal that an eruption is becoming more likely. It is like taking the volcano's temperature to see if it's running a fever. By combining data from ground movement, gas emissions, and thermal activity, scientists build a comprehensive health report for the volcano. But here's the million-dollar question. With all this technology, can we predict eruptions with perfect accuracy? The honest answer is no. Volcanic forecasting is a game of probabilities, not certainties. Every volcano has its own unique personality and plumbing system. Some give clear warnings for weeks or months, while others can erupt with very little notice. Scientists can say an eruption is likely within a certain time frame, days, weeks, or months, but they can almost never pinpoint the exact hour or day. It's more like forecasting a hurricane than predicting a train schedule. You know it's coming, you know it's dangerous, but the exact path and intensity can change. Let us look at a case where forecasting was a massive success. The 1991 eruption of Mount Pinatubo in the Philippines. For centuries, Pinatubo was quiet. But in the spring of 1991, it roared back to life. A team of Filipino and American scientists raced to install monitoring equipment. They saw the ground swelling, detected huge amounts of sulfur dioxide gas, and recorded thousands of small earthquakes. Based on this overwhelming evidence, they convinced the government to order a massive evacuation. When Pinatubo finally unleashed one of the largest eruptions of the 20th century, over 58,000 people had been moved to safety. It was a landmark achievement for volcanology, proving that science could indeed save lives. Now let's jump to a more recent example. The 2018 eruption of Kilauea in Hawaii. Kilauea is one of the most active volcanoes in the world, but this event was different. For weeks, scientists at the Hawaiian Volcano Observatory watched as magma drained from the summit, crater and migrated underground through the volcano's east rift zone. They used GPS and satellite data to track its path, warning residents in the Puna district that magma was heading their way. When the lava finally broke through the surface in a residential neighborhood, authorities were prepared. While over 700 homes were destroyed, the timely warnings and evacuations meant that there were no fatalities directly caused by the lava flows. Kilauea showed us how real-time monitoring can guide emergency response even in a complex evolving crisis. But this brings us to a tricky issue known as the cry-wolf problem. What happens when scientists issue a warning and nothing happens? Evacuating a city is incredibly disruptive and expensive. Businesses shut down, people are forced from their homes, and the local economy takes a massive hit. If an eruption doesn't occur, people can lose trust in the scientists. The next time a warning is issued, they might not take it as seriously, which could lead to a catastrophe. This puts immense pressure on scientists and public officials. They have to weigh the risk of the volcano against the social and economic cost of a false alarm. It's a delicate balancing act with lives on the line, so what does the future hold? We live on a volcanically active planet, and massive eruptions are not a matter of if, but when. Scientists use the Volcanic Explosivity Index, or VEI, to measure the size of eruptions. Pinatubo was a V6. An eruption of VA7 or even a supervolcanic VA8 would be a global event, capable of altering the climate and disrupting society on a scale we've never seen. The last VA7 eruption was Mount Tambora in 1815, which caused the year without a summer. We know these events are inevitable in our planet's long geological story. This is why continued research and investment in global volcanic monitoring are so critical. By improving our sensor networks, refining our predictive models with machine learning, and fostering better communication between scientists and communities, we can become more resilient. Understanding the signs our planet gives us is our best defense against its most powerful forces. The work of volcanologists isn't just about fascinating science. It's about preparedness and protecting our future on this dynamic and incredible Earth. Thanks so much for joining me on this journey into the world of volcanoes. If you found this fascinating, don't forget to hit that like button and subscribe for more deep dives into the science that shapes our world. See you next time. The resource disparity is stark. Wealthy nations can afford sophisticated monitoring networks with dozens of seismometers, GPS stations, and gas sensors feeding data to well-staffed volcano observatories. Developing nations, where many of the world's most dangerous volcanoes are located, struggle to maintain even basic monitoring equipment. Indonesia, which sits atop the Pacific Ring of Fire and contains more active volcanoes than any other nation, has made heroic efforts to monitor its volcanic systems. But resources remain limited. When eruptions occur in remote areas, the first warnings often come from villagers reporting ashfall, rather than from seismic networks detecting precursory earthquakes. The social dimensions of volcanic risk are equally complex. Population growth continues to concentrate people in volcanic hazard zones. The slopes of volcanoes offer fertile soil, mild climates, and access to geothermal energy. Naples grows closer to Vesuvius each year. Towns around Yellowstone expand as people seek recreation and natural beauty. In Indonesia and the Philippines, millions of subsistence farmers cultivate volcanic slopes because that is where they can grow crops. Telling them to relocate is not a viable solution when they have nowhere else to go and no economic alternatives. Cultural factors further complicate risk management. Many communities living near volcanoes have done so for generations, even centuries. The volcanoes are integrated into local identity, mythology, and spiritual practices. Mount Merapi in Indonesia is considered sacred by the Javanese people. The volcano's spiritual guardian, the gatekeeper known as Ma Meridian, refused to evacuate before the 2010 eruption and died in the pyroclastic flows, along with 32 others who had stayed with him. Convincing deeply traditional communities to abandon their homes based on scientific data requires cultural sensitivity and trust that takes years to build. The economic implications of a major volcanic eruption in the modern globalized world would be catastrophic. The 2010 eruption of Eyjafjallajökull in Iceland was a small, VA4 event that produced relatively minimal local damage. However, the volcanic ash disrupted air travel across Europe for 6 days, grounding 100,000 flights and stranding 10 million passengers. The economic impact exceeded $5 billion, primarily from lost business and tourism revenue. This was from a moderate eruption in a sparsely populated area. A VA6 eruption near a major population center would disrupt global supply chains, financial markets, and transportation networks for months. Climate impacts represent another underappreciated risk. The 1991 Pinatubo eruption injected approximately 20 million tons of sulfur dioxide into the stratosphere, lowering global temperatures by 0.5 degrees Celsius for 2 years. This provided a temporary reprieve from global warming but also disrupted weather patterns, altered monsoons, and contributed to crop failures in parts of Africa. A V7 eruption would inject 10 times as much sulfur dioxide, potentially triggering global cooling of several degrees for multiple years. The agricultural impacts would be severe. Modern industrial agriculture operates with minimal reserve capacity. Consecutive years of shortened growing seasons would quickly exhaust food stockpiles and trigger humanitarian crises. A VA8 supereruption would effectively end modern civilization as currently structured, at least temporarily. The immediate impact zone, extending hundreds of kilometers from the eruption, would be rendered uninhabitable. Ashfall would bury regions thousands of kilometers away. Global air travel would cease. The sulfur dioxide aerosols in the stratosphere would trigger volcanic winter lasting years to decades. Agriculture would collapse across much of the planet. The resulting famines would kill more people than the eruption itself. Billions would be at risk. Yet, even facing this existential threat, humanity has developed no coordinated international response plan. Unlike asteroid impact risks, for which NASA and other space agencies maintain detection programs and have developed theoretical deflection strategies, volcanic risks receive comparatively little attention at the international level. There's no global volcano monitoring network. There is no international rapid response team for volcanic crises. There is no strategic reserve of food and supplies positioned for a post-eruption world. Some scientists advocate for increased investment in volcanic monitoring and research as insurance against low probability but high consequence events. The cost would be modest compared to the potential losses. Expanding monitoring networks to cover all high-risk volcanoes globally would cost perhaps $1 billion, less than the price of a single advanced military aircraft. Yet, securing funding for such initiatives is politically difficult when the threat seems abstract and distant. Others argue that certain risks, including V8 supereruptions, are so catastrophic that traditional mitigation strategies become meaningless. No evacuation plan can save billions of people. No food stockpile can sustain global populations through years of volcanic winter. In this view, the appropriate response is acceptance of fundamental uncertainty and vulnerability, combined with efforts to build societal resilience through decentralized food production, preservation of agricultural knowledge, and maintenance of seed banks that could allow rebuilding after catastrophe. The philosophical dimension cannot be ignored. Humans evolved to respond to immediate threats, not to abstract risks that might materialize in centuries or millennia. Our political systems operate on election cycles measured in years, not geological timescales measured in tens of thousands of years. Asking societies to invest resources and make sacrifices for events that might not occur in our lifetimes or our children's lifetimes, or even our great-grandchildren's lifetimes, runs counter to human psychology and political incentives. Yet the Earth does not care about human psychology or political cycles. The magma chambers beneath Yellowstone, Campi Flegrei, Toba, and Long Valley continue to accumulate melt. Pressure builds imperceptibly. The crust flexes and fractures. The systems evolve toward eventual eruption according to the laws of thermodynamics and fluid mechanics, indifferent to human presence or concern. We stand at a unique moment in Earth's history. For the first time, a species exists with the technological capability to understand these processes, to monitor them in real time, and to anticipate future eruptions years or decades in advance. Yet we also possess the capability to ignore or mismanage these risks in ways that could make natural disasters far worse than they need to be. The choice ultimately is whether we will use our knowledge wisely investing in monitoring research and preparedness, or whether we will gamble that catastrophe will remain someone else's problem in some distant future, and hope that we are not the generation that loses that bet.